Greetings, everyone. This is Akon Raman from Tennessee Technological University, and I will be presenting our paper titled The S Code Activities, Development Anti-Patterns for Infrastructure as Code. This paper is in collaboration with Ifat Farhana and Lori Williams from NC State University. The paper is currently published at Empirical Software Engineering Journal and was accepted as a journal first paper at ISEC FSE. The paper is about infrastructure as code. Typically, for configuration management, practitioners have used bash scripts. So they develop their own custom scripts, execute them to manage their computing infrastructure and cloud infrastructure and manage their configurations automatically. Infrastructure as code is the practice of doing it using dedicated syntax. So this is the new normal amongst practitioners, and which says that instead of considering bash scripts as an isolated artifact of software engineering, it should be developed in a systematic manner using a dedicated syntax, and all the best practices of software engineering should be applied. From a very high level, let's try to demonstrate what infrastructure as code is. So let's assume that there's the system administrator who has to provision 10 Azure instances. One way of doing things is the administrator writes one script, executes it manually, and repeats the whole process multiple times. This is error-prone and susceptible to introduce problems. In comes infrastructure as code, where the practitioner writes one script, executes it once, and all the infrastructure gets provisioned automatically. In this manner, the whole process becomes automated, less time-consuming, and also less error-prone. Automation is not the only thing that is related with infrastructure as code. It also incorporates the good software engineering practices such as version control and quality inspection, such as applying linting tools, applying security analysis, and mitigating bugs and security weaknesses. This practice is getting more and more prevalent and commonplace amongst information technology organizations. So here are some examples where different organizations who belong to different sets of domains, such as finance and energy and science, have used or are using infrastructure as code and has received benefits. So for example, Mozilla was able to reduce its manual effort by 99%. Ambit Energy was able to increase its deployment frequency by a factor of 1200. ICE, which stands for Intercontinental Exchange, which manages New York Stock Exchange, reduced its provisioning time from 1 to 2 days to 21 minutes. And then NASA, the space organization, was able to reduce its patch release time from multiple days to 1 hour. So all of these examples that showcase that infrastructure as code, or ISC in short, has multiple benefits and is becoming more and more commonplace. However, there is a problem of related to defects. So what happens when defects appear in infrastructure as code scripts? Due to its execution nature, it gets propagated into all instances that are being provisioned using infrastructure as code. And defects in infrastructure as code has consequences. So here are two examples. One is from AWS, Amazon Web Services. So a defect in an infrastructure as code resulted in service disruption for the Amazon S3 service. GitHub experienced some similar kind of service outages as well. So in the case of GitHub, a defect in an infrastructure as code script caused a domain name service DNS outage. So these two examples showcase that defects in the infrastructure as code scripts are commonplace and can cause large-scale consequences. What practitioners would like to see is that the defects in ISC scripts are mitigated. So that green box corresponds to a set of activities that will mitigate the defect, and upon execution of the defect-free ISC script, the provisioning will maintain quality and will satisfied and will result into desired results. So in our present paper, what we focus on, what should be in that green box. So what activities should developers adopt, or avoid so that defects in ISE scripts are mitigated. So when we started the study, we came across this particular defect example where the wrong package name was provided in a commit, and the commit was 460 lines in size. And this got us thinking if submitting long size or large size commit is related with defect or not. So we wanted to systematically identify a set of development activities such as submitting large size commits and see if those activities are correlated with defects or not. So we refer to these development activities as development antipatterns. So more formally, these are recurring development activities that correlate with defective IC scripts. And the goal of our study was to improve the quality of IC scripts by identifying development activities that correlate with defective IC scripts. So we answered the following 3 research questions. First one is what development activities are related quantitatively with defective infrastructure as code scripts. Then we wanted to see what the practitioner perceptions are through a quantitative survey and also a semi-structured interview. And then we also wanted to see if we build defect prediction models using these development activity metrics, then what do the results look like. The implication of this particular research question is that it gives a way for practitioners to automatically identify which scripts are likely to be defective or not using machine learning. So to conduct our empirical study, we started with a data set, which was where we extracted commits from IC repositories, applied qualitative analysis, and then there was a whole curation process involved to build a defect data set for ISC scripts. Then for RQ1 to identify which development activities are related with defective ISC scripts, we first found out a set of metrics that correspond to a development activity. And to find out that set of metrics, we did a scoping review. We did a scoping review of publications related with defect prediction, fault prediction, and published at top-tier venues such as ICSE, FSE, and the CCS. So the idea was from prior work, we will be able to obtain a set of metrics that are actionable, that can be mined from version control repositories, and are actually related to development activities. So after doing the scoping review and selecting the metrics, once we came up with a set of metrics that we mined systematically from open source repositories, and then from the metric mining and from our data set, we conducted a statistical analysis to identify the relationships between the set of development activity metrics and defective IC scripts. For RQ2, what we did was from the same set of repositories, we mined emails and then sent surveys to practitioners. And from the survey, the practitioners who responded, we then invited them to do semi-structured interviews, so that we get deeper insights on the perceptions of practitioners for the identified set of metrics. And finally, for the defect prediction construction, that was done by getting the metrics, applying feature selection such as PCA, principal component analysis, applying statistical learners, and then evaluating the performance by comparing against existing methods. So this is a summary of our data set. Our data set comes from 4 organizations, has a set of around 2,000 scripts. The distribution of defective scripts is around 50% for our set of scripts. So from a scoping review, we are altogether identified 7 metrics. They are developer count of developers who modified a script, disjointness that corresponds to how one group of developer is separate from another group of developer or multiple groups of developers, the amount of code that is being done by the person who is contributing the most to a file or to a script. Then minor contributors are referring to the developers who are contributing less than 5% of the total code. The normalized commit size is the number of additions and deletions within a commit, and then scatterness corresponds to how scattered the written lines are, and then unfocused contribution is a measure which measures how many developers are modifying how many files. So after doing the statistical analysis, we found out that these are the metrics that correspond to different 5 development activities, namely developer count. So defective scripts are likely to have more developers. Defective scripts are likely to have more disjointness between developer groups. Defective scripts are likely to have less amount of highest contributors code. Defective scripts are likely to have more minor contributors. Defective scripts are likely to have more unfocused contribution. So from these metrics that correlate with defective IC scripts, we are able to identify 5 development anti-patterns for IC script development. For the survey, what we did was we sent email to 250 practitioners, 51 responded, and then out of the 51 survey respondents, 11 agreed to do a semi-structured interview with us. So the survey results indicated that scatterness and normalized commit size, the 2 metrics that did not show correlation with defective IC scripts, to be more prevalent with respect to practitioner agreement. So it had the highest practitioner agreement as demonstrated on the right-hand side. And the lowest agreed upon metric was unfocused contribution. So this counterintuitive result motivated us to systematically look into the responses from the practitioners from our semi-structured interviews, and then identify what could be the possible reasons for agreement and disagreement. So on the right-hand side, you see agreement reasons, and we notice that a set of agreement reasons are common across metrics, and practitioners think that the same set of reasons are applicable on why they agreed or disagreed a metric to be related with defective IC script. For example, communication problems. Because of communication problems, the practitioners think that developer count and high developer count and high disjointness between developer groups could be correlated with defective IC scripts. For lack of context, developers think that highest contributors code, having lower amount of highest contributors code and high amount of minor contributors, could be related with defective IC scripts. Normalized commit size and scatterness is related with defective IC scripts according to practitioner perception, because it could introduce difficulty in code review and debugging. And finally, unfocused contribution is related with defective IC scripts because of distraction. So if one developer is working on multiple files, then due to distraction, the practitioner could introduce a defect or multiple defects in a script. We also identified why practitioners would disagree a particular metric to be correlated with defective IC scripts. So practitioners think that because of knowledge sharing, developer count, disjointness, highest contributors code, and minor contributors are in fact not correlated with defective IC scripts. Developers also think that due to experience of developers, normalized commit size is not correlated with defective IC scripts. And similarly, due to lack of context, scatteredness is not correlated with defective IC scripts. And finally, bubble problem, which is where one practitioner is only working on one script and does not focus on other artifacts, other scripts, or other parts of IC development. Unfocused contribution is not actually related with defective IC scripts. So finally, for our defect prediction results, we observed that use of development activity metrics has some promise. So as shown in the deep green bars in this particular bar plot, we see that it outperforms existing methods, namely prediction models constructed using text mining features and code metrics. It outperforms those 2 techniques. However, it remains almost the same for one data set, namely Mozilla, and it remains, it is lower compared to code quality metrics for Wikimedia. And similarly for another measure, namely recall, we see that the prediction performance using development activity metrics is overall better for 3 data sets, but not for the Wikimedia data set. And finally, for the F1 measure or F-score measure, we see that the defect prediction models constructed using development activity metrics is best for 2 data sets, comparable with another technique for 1 data set, and lower than our baselines for the Wikimedia data set. So in summary, all these results pinpoint that use of development activity metrics to construct defect prediction models has some promise, but it will require some more effort to make it more applicable and usable in the context of IC development. So what are the implications of our study? So from our empirical study, we have identified a set of development anti-patterns that developers could consider while they're developing IC scripts and managing their IC development process. We observed that there are nuanced perspectives when it comes to what particular development activities could be correlated with defective IC scripts. So adoption and integration of our development anti-patterns into an organization would require deep understanding of the context, the organization that we are thinking of. So we need to be mindful of how they perceive these development activities with respect to correlation with IC script quality, and how can we build upon our studies so that we can identify a comprehensive set of development anti-patterns. And finally, defect prediction models can have implications on how we can prioritize different artifacts or IC scripts that are more likely to be defective for efficient allocation of verification and validation efforts. A few limitations of our study: conclusion validity. We have rater bias in anti-pattern derivation because the scoping review was done by the first author, so there's some bias involved. The data set and data set size is limiting. External validity, we use open source data sets, so our results might not hold for proprietary data sets. And construct validity, the data set was constructed using graduate students, so there's some inherent bias related to that as well. So in short, we talked about the importance of mitigating defects in IC scripts. Then we talked about how we can identify development anti-patterns using quantitative analysis. Then we also talked about what are the perceptions of practitioners about the development activity metrics. We discussed how our results could be useful for software